Okay, the general design process. First, like any subsystem, you want to allocate your mission and system requirements. You can break this step down into establishing functional requirements of your avionics system based on your mission phases, your payload requirements, and spacecraft bus requirements. You'll see here that we have all of the different subsystems, their components, and then up here in this table, the column headers are different performance metrics that you could possibly consider to inform how to design your onboard computer or your other avionics. So we have throughput estimation, which is the amount of data that you can possibly shove through a channel. CPU utilization, which is the amount of processing power you want. The amount of memory. The update frequency, so this relates to real-time operating systems. Sorry, timing accuracy relates to real-time operating systems, and update frequency is how frequently you ping different subsystems. So you see here, we were talking about spacecraft bus requirements. For each subsystem, the functional requirements are going to be different for these different performance metrics. The payload is usually the most demanding, but you'll see that there are other subsystems like the communications or telemetry and control subsystem that has a high memory requirement for the transmitter. Okay, you can then evaluate candidate architectures. We'll be talking about avionic components next lecture. You can develop block diagrams to make sure you meet your functional requirements. You can conduct trades and determine feasibility. We'll talk about avionics reliability and fault tolerance at the end of the week. And then you can also develop non-intrusive testing methodologies. It's good to do this to think about how you would test your system so that you build a system that is verifiable. Okay, so once you have your requirements set, you can think about different operational modes and states. Recall this state transition diagram where you want to develop a state diagram consistent with your functional requirements. This could help you define the power cycle and duty cycle for low-level computer and high-level computer modes. You can model different operational stages as different states. Your concept of operations will give you operational states or phases, and you can formalize this as distinct states, where a distinct state would be, say, one of these bubbles. Following this state diagram, you can follow and model failure states, the progression of different failures, and then you can consider the effects on your ground operations for all the states. Using this state diagram, you can think about, do we want to make it manual or autonomous? When in the schedule are we going to, say, come into a state that needs a manual transition versus an autonomous transition? Okay, so after getting the high-level requirements and the different modes of operation defined, we can functionally partition and allocate the computational requirements that is asked of the onboard computer, and then the interfaces that go to the other subsystems. So this could manifest as the functions and requirements between the spacecraft bus, the payload, space and ground, and you can specify in these subsystem requirements hardware and software requirements. once you have those hardware and software requirements down, then you can start thinking about the interfaces between the components. These interfaces come as input and output requirements. There are documents called interface control documents that define the interfaces. So remember, we were talking about there are physically different connectors. There are physically different I/O connectors, but on the software side, there's also different message packet formats. So you also have to encode that in. These are different block diagrams of different. So this one is a microcontroller block diagram. You'll see here, so CAN bus, that's a data bus. USART1, USART2, those are different I/O connectors. Let's see, what else? SBI is another connector. So you can see here, there's a lot of data that's being passed, but also a lot of interfaces that need to be consistent and managed. GPIO is also another I/O. And those, it looks like, are going to different subsystems. Let's look at the diagram on the right. Okay, so this block diagram, let's just break out some notable parts. Here is a board for payload data handling, and it interacts with a bus, a data bus. You'll see later on in the chapter, we talk about different data buses. This one looks like it's the MIL standard bus. So a lot of different packets are being communicated onto that bus. You'll also see that this payload data handling board is communicating to a bunch of instruments across these different lines. It's also communicating with comms and power. So yeah, the CDH avionics lead would help in the design of things like this with equal contribution from the payload lead. Okay, so this is the last step in the general design process where you actually select your baseline architecture and form the baseline system specification. This is where you actually take your requirements and you translate them into solutions. These solutions can be defined by these design specifications, like your sensor list, your network strategy, your throughput estimate, your communications bandwidth. And then you can select critical components. This will define the amount of data that you need to manage, what kind of redundancy strategies you need to apply to these critical components, and the different communication frequencies. So if you look at the previous, just one note of subtlety, this 1553 MIL standard bus, it has 2 lines. You'll notice that for a lot of buses, there are multiple lines to add that redundancy. And you'll see that over and over again in block diagrams. So that's just like a bit of nuance that maybe you'll see. This is a block diagram where the command and data handling section is pretty much this right side of the diagram. You can see there is a ton of different components that you need to, that you're responsible for. Like the previous slide, there's an instrument interface. There's going to be processors. There's going to be some interface with the communications subsystem, which is physically here. But yeah, this integrated electronics module has the processing, has the interfacing with all the other subsystems. Yeah, that's all I want.